Have you ever wondered how ChatGPT deals with words or concepts that it's never seen before? Here, I'll ask it to interpret a made up word, and you'll see that it breaks it down into different syllables and analyzes each of them to try to figure out what the word means. Now, many people think that LLMs will process their inputs as sequences of words and punctuation, but that's not really how modern LLMs have processed inputs for years. Instead of encoding entire words and just adding an unknown word if they didn't know what the word was, they would actually break the word down into smaller and smaller pieces, and they call this byte pair encoding, or BPE, where they have a vocabulary of about 50,000 different tokens that it can reduce down to, so there is nothing that is ever unknown. And you can do this tokenization yourself using a Python library like TickToken, or you can go right onto OpenAI's website on their tokenizer, and you can visualize how each of the versions of GPT tokenizes a word. After you've converted your string into a bunch of tokens, you're going to want to convert that into something more meaningful. Now, one data structure that can represent meaning a little better is a vector, just like you would deal with in physics, where you have 3 dimensions to represent a location in physical space. We instead used hyperdimensional space, often with 12,000 or more dimensions. And that space, if we map a token into that space, other tokens that appear in similar contexts will be clustered close together. And so that way we can have a system that actually kind of conveys meaning and relationships between tokens. Now, in order to get these vectors, we need to train what we call an embedding layer. Once the LLM is trained, this embedding layer will take in a token ID and it will output a vector. But this new vectorized token embedding doesn't contain any word ordering. So just by looking at this token embedding, if you wanted to take the phrase, "the fox jumped over the dog," and ask a question, "who did the jumping?" you wouldn't be able to answer that with just the token embedding because it doesn't have that position data. Now, this is why we build a separate position encoding that encodes this additional sequence index. So then the token embedding and the position embedding can be added together to create an input embedding that represents both identity and position, which can then be passed to the subsequent transformer layers to infer things about relationships and grammatical structure. Now, although the training objective was merely predict the next token in a sequence of tokens, the system's internal representation of information is based on syntactic roles and semantic similarities. Now, consequently, the model is able to reason about new words and problems and ideas not because it memorized them, but because its geometry captures the abstract regularities of language.